So let's wait for 5 more minutes to see if other people join. Then we'll start at 3:05. Meanwhile, if you have any questions regarding the previous session, you can ask.
Hello, sir.
Hello. Yeah, hello. So we'll
You have asked that why if BJT is VCC
no, I
or
had asked
CSCS.
that. I had asked that if BJT is a VCCS or CCCS. So did you
Yeah, yeah.
find the answer?
Okay, I analyzed that. Okay, you asked your own analyzation, right?
Sorry?
Our self analyze.
Can you please repeat the
You asked
question?
and you asked why also.
Yeah,
in
yeah.
our
Why also?
analyzation.
You have to be able to explain your answer, whatever choice you make.
Okay. Okay. In my opinion, I will tell that in when in circuit theory we explain that CCCS or VCCS VSCS to be it should be linearly dependent.
It should be linear. Yeah, yeah. Linearity should be maintained, right? Go on.
Should be maintained. So it is current controlled. If in voltage control, there will be an exponentially dependent, right? That's why we
Not
say
really.
current
See,
control
no, no, not really. See, what we are talking about is that the small signal sense, right? Both cases. So in small signal
yes.
case, your linearity will be preserved. So whether it is VCCS, you treat it as a VCCS or you treat it as a current controlled source. So it is quite the same thing. If you see the models like your hybrid pi models for small signal and your T models, then you can interchangeably use these terms. Okay, so there is no hard and fast go that if it is a VCCS or it is a CCCS. It depends on so many factors. For example, what kind of configuration you are using, the amplifier, and what kind of small signal models you are using, right? So your IBE can control your IC also, your VBE can control your IC also. We'll see today, right? In through large signal models. I think small signal models have not been detailed in the week 2 lectures. So large signal models, we'll see that how those models came about. Okay. So please
Okay.
hold that discussion till then. Okay. So yeah, welcome everyone. This is NOC24W139 Microelectronics Devices to Circuits. The instructor is Professor Sudev Dasgupta from IIT Roorkee. I am Debashish Nandi from IIT Kanpur. So as you know that this goes live every Sunday 3 to 5. There may be 1 or 2 week exception that we will inform you a priori. So the duration is 2 weeks. This is the second week. So as already iterated earlier that there are certain prerequisites which I want you to follow, that I at least expect that whoever is doing this course are serious students, or they want to enhance their understanding of the device physics and circuits. So please at least you should have gone through the lecture videos of the previous week and attempt the assignments by yourself once. Then it will be easier for you to follow the discussions. Okay. And also if you have any rough paper and pen along with you, we have all our scientific calculators in mobile phones only these days, so it will be better if you follow along with me, right? Or write down some key aspects what we are discussing. Okay, so let's start. This is week 2. So first question is that before going to the first question, let me just ask you one thing. This I intended to cover last day. We see these PN junctions are drawn, these BJTs are drawn like this, right? So can anyone tell me that is BJT a planar device? How the technology is about? By the way, what is a planar device and what is a vertical device? Means do BJT look like this only in real life when you fabricate them?
No, sir.
So how does it look like?
It are actually it is vertical, like they are being fabricated first N, then P, then N.
Okay, you mean to say we will have a N plus, then we will have a well of, let's say this is your, so what is the bottom part? Which one is that? Emitter or collector? What is the substrate that we will work on?
Sir, bottom part is base, then we come emitter, then
I think
inside
not.
collector comes.
So this is your collector, right? Let's say this is your the lowest doping part. Then you diffuse or ion implant a region. This part you have what? This is your P plus, right? And this part will is remaining as your emitter. So this will be your N plus plus. So this is your emitter. This is your base, and this will constitute your collector. Okay. So BJT can be fabricated in a planar device. What do you mean by planar device? You can see that all the contacts are on the same plane. Okay.
Okay, sir.
So then why do we uh, draw the device like that? What are the approximations we make? Last time we have discussed that the doping profile is something like this, right? You have a very high doping profile in emitter, then a moderate doping profile in base, then a small doping profile in collector for a very narrow region. Then this profile goes up and matches that of the emitter, right? So this is your doping profile of, let's say, doping. So this, let's say 1E20, 1E means 10 to the power 20. Then it is 1E18, let's say then it is 1E16, and then it is again 1E20. So this is your emitter, this is your base, and this entire stuff is your collector. Okay, now you consider that this there is a cut section along this way. Okay, let's say this is what you are seeing right now. So what will you see? You will see a structure something like this, right? If you just draw it, you will have a this, this, then this. So this will be your N plus plus, this is your P plus, and then this is your N, right? You have, let's say for the sake of convention, I draw the contact at this point for pictorial representation and base at this point. Then you flip it over horizontally, then you get this kind of structure, okay? So this is how the physical device is fabricated, and you will see that in modern devices there are other stuffs below this also, right? For example, isolation with the nearby device. How do you do that? Otherwise, your two collector get connected, right? So you provide a another p-type layer inside and then another n-type layer. So this will always be in reverse biased. So these are given for isolation with nearby devices, and also it provides you the mechanical stability, right? These wafers are very thin. For example, let's if I take this point is 0, then this will be these dimensions are typically, let's say this is your 2 micrometer, let's say this will be your 3 micrometer. You see that your base is obviously should be narrow. We have discussed this last time, and we'll also touch upon it today. And this, let's say your 10 micrometer, and then this entire stuff, let's we have to break here, otherwise I cannot write on the same scale. Let's say it is 200 micrometer, right? So you see we are talking about just this much of the device. So when you go to the physical device, there will be so many other effects. For example, let's your base contact is here, right? But you are considering your transport at this point. So there will be a series resistance associated with this. This we call as RBB. So this will come into picture in your high frequency stuffs, right? And there are other capacitances involved. Capacitance involvement will also be there. That will determine your FT, means unity gain frequency, F max, etc. of the device. Okay. So that is one thing. Another thing is that, yeah, so it is asked that, so yeah, let us discuss about the regions of operation. Okay, so what do we have in BJT? We have two junctions, right? One we call as EBJ, that is your emitter base junction. Another junction is your CBJ. So based upon the condition of these two PN junctions, we can have four regions of operation in BJT. So what are those? So regions of operation. So what do we have? We have EBJ, we have CBJ, and then we have operation mode. So let's start with both are reverse biased. Then what will happen? What is the operation mode? Anyone? You can unmute and
Cut
answer.
off.
Why do you say so?
There is no current.
Why there will not be any current? Why, let's say, let's take your emitter based junction has to be forward biased. Why do we need that?
The
Yeah, you can unmute and answer.
the electrons are holes are coming from emitter to base,
Yeah, let's take it an
so that
NPN junction
it should be
transistor, so electron will be
forward.
coming. So you need to have then
Right.
injection of carriers, right? Across this point.
Yes.
So we know that in PN junction, we have to have forward bias over and above equilibrium to have a injection of carrier so that my excess minority carrier can reach at the other side, right? And how does that happen? If you remember your PN junction band diagrams, so let's say this is your P side and this is your N side, or I should draw it differently because NPN I was talking about, right? So this will be, let's say this. So how does your carrier move? You have a metal contact at this position, right? Now you are applying, you are making this junction a forward biased, right? So what will happen? Your energy barriers will come down, right? So once your energy barrier, this is your applied forward bias. Okay, yeah, this is your applied forward bias. Let's say this is QVBE. Okay, this is your emitter, this is your base. So if this much energy is reduced, and what happens? This is what scale is this, by the way, in band diagram? What is this
Energy.
axis? What energy? Energy is
Energy.
not sufficient. It is electronic energy, right? It acts weirdly, differently, that of a voltage. Means voltage when you talk about, or potential when you talk about, last class I mentioned the definition of the potential, right? In any field, and you need positive charge, you need to bring out from infinity to that field. How much work done you need, how much work you need to be done, is that is the definition of the potential, right? So potential is associated with a positive sense. That means if I tell you that this point has a higher potential than this point, you can easily tell that this point has higher amount of positive charges in some sense, right? But in energy band diagram, what we do is that we plot the electronic energy. That means if I apply positive bias or forward bias, so rather forward bias means what? P type will be positive with respect to N type, right? So this band, instead of going up, it will go down because your these bands are minus q times phi, right? Because we are talking about electronic energy. Do you see? Anyone who has difficulty to follow? Okay. So what happens is that now it is your energy, right? So can anyone do anyone remember what is the Fermi distribution? How does it look like? It is something like this, right? So can anyone tell me that what is this axis of Fermi distribution? That means let's say this is your f of E, and this is your energy, right? So can anyone tell me how does the Fermi distribution look like? Let's take a point at EF. It will be somewhat around this point. Let's say somewhat minimum point, zero point 0.5, around zero point 0.5, let's say. And then what will happen at as we go to lower energy, you will reach maximum probability. As we go to higher energy, obviously carriers try to occupy the lesser energy, so at higher energy the probability will be lesser. So this will be your plot, right? Now if I plot the same thing on this, our electron, this is your EC, this is your EV, so our electrons are on conduction band, right? So what will we have? We will have something like this scenario of Fermi distribution. So now think that you are seeing an energy barrier, up to this. So only these electrons, these hot electrons were able to pass earlier in equilibrium, right? Now to have a significant current flow, what you do is that you, by applying this forward bias, you pull the energy barrier down. So your difference is now, energy barrier difference is now reduced. So what happens is that this additional electrons, this additional shaded part, this part also can now travel over the barrier. So basically you are injecting these carriers in the other side or from emitter to base. So you need to have a forward bias there to have a significant amount of current. Okay. So this is just a brush up of your basics. I know most of you know this stuff. So if both the junctions are reverse biased, then you have the operation mode, as rightly pointed out by someone, is cut off. Then what about if my emitter based junction is reverse biased and collector based junction is forward biased? What is that mode called?
Reverse active.
Reverse active, right? Again, same thing. Reverse active means your emitter based junction is reverse biased and your collector based junction is forward biased. That means what are the consideration you made by making this stuff highly doped, this stuff less doped, all thing are reversed. That means it is a very bad transistor, right? It is a transistor, but it is a very bad transistor in active region. So this is an reverse active mode. So there are very niche applications in earlier days when reverse active modes were used. Nowadays, this mode is just not used at all for that sake. And what is this mode? This is the most common mode of a transistor application.
Forward active.
This is forward active, right? And this is the region where your most of the amplifiers work on. And what about when both of them are forward biased?
Saturation.
Saturation, right? We'll see that why it is called saturation and what are the large signal models of saturations. Okay. So now what is happening? Last class I have told you how to read the notation of the transistor. So this is an arrow this side. So this will be your P side. This will be your N side. So obviously this will be your P side. This will be your N side. So it is an NPN transistor, right? So this is between emitter and base junction. So this is your base. This is your emitter. This is your collector, right? So assuming that it is a silicon diode, So assuming that it is a silicon diode, so what is the condition required? What is the condition on this? This is an N type, this is an P type. So N type is higher at higher potential than your P type, because N type is at 5 plus 5 volt, P type is at plus 3 volt. So what is the condition in this junction?
Reverse.
So it is reverse biased, right? And what about this? Obviously, this is your 3 volt and this is 2 volt. So this voltage drop is greater than your cut-in voltage of the diode, right? Around zero point 0.5 to zero point 0.7, depending upon what current value you are taking, right? So that voltage, so this makes this diode in forward bias. So now you have your emitter based junction in forward biased and your collector based junction in reverse biased, right? So the mode of operation is forward active. So now given this table and configuration, so given any voltage like this, will you be able to tell me that uh, you can tell the mode of operation, right? If you are given the bias and if you are told what kind of material, base material is that, means if it is silicon BJT or germanium BJT or gallium arsenide BJT, because all of them will be having different cut-in voltage range, right? So two things to note here. One thing is that what is the type of the BJT, of which semiconductor it is made of. Second point is that what are the conditions on the junctions, if it is forward biased or if it is reverse biased, right? So any question, anyone?
Hello.
Yeah.
Yes, sir. I want to ask in this profile. Uh,
Okay.
sir, yes, sir. You have told that a base should be less doped, but in
No,
here
no.
in the profile,
Collector should be least doped.
collector should be least doped.
Yes. You see that profile, right?
Yes.
This is highest, then this is, then this a very small region in the collector, you have the small doping. Then to avoid the series resistance drop, because if you, what is your resistance? Resistance is proportional to rho, right? That means 1 over sigma. Sigma is proportional to your n doping times charge times mobility. So if you reduce your doping in the collector, your resistance will increase. To avoid that, what you do, you make a very small region in the collector less doped, and then you have a sudden jump in the doping similar to the order of emitter.
Okay, sir.
So yeah, in this context, we are discussing about this, right? Amplifiers. So yeah, so we are discussing about, we will be discussing about amplifiers today. So it is a right time to discuss that why forward active region is used as amplifiers and how come BJT amplify. So it is an open discussion, so anyone can chip in. Okay. So the question is, what we are asking is that why BJT, for that matter, okay, let me put it this way. Why BJT can be used as an amplifier. Okay, question number one. Question number two is why forward active mode. So, what is the most important thing that is required for amplification? Can diode give me amplification? And what kind of amplification we are talking about? We are talking about power amplification, right? If I put a small signal, so my output should be something bigger, right? So this amplification we are talking about. So let's see it in this way. Let's say if you have a block, right? Last class we had discussed that why your three terminal devices are required, right? For transistor action. So now let's say you take a linear network, okay? And you, this is your V1, let's say this is your V2, let's say this is your I2, let's say this is your I1. So what is your P input? Power in is your V1 times I1, right? And what is your P out? P out is your minus V2 times I2, right? So can you comment on the relative magnitude of these two things? Means if your P in will be greater than P out or P out will be greater than P in. What do you think?
Equal.
Why equal? You have a linear network inside, right? That network has to have some losses. So this network will obviously incur some losses in terms of maybe heat. Okay. So always your P out will be less than P in. So do you agree with this statement? You are putting some power in and you are taking some power out. But this, to that system to work, there will be certain amount of losses because the resistance cannot be zero, right? It has to have some finite resistance. So your P in is always greater than your P out. Now let's assume that this V1 has two parts. Okay. One is your, let's say this is your DC part, and there is a very small, this is your signal. So this we called as bias, this we called as signal. Similarly, your V out will also have, let's say your, this is your signal and this is your V20, this is your DC bias. Okay. So if your network is linear, right, superposition will apply. So this signal part will directly translate to this signal part, and this DC part will directly translate to this DC part, and then you use the superposition. That means your P out now has two components, right? One is your signal, let's say P out signal, and this is your DC, P out DC. Similarly, you will have this part, signal and DC, P in signal and your P in DC, right? So if the network is linear, then what will you have? You will always have, based upon this connotation, you will always have your P out signal is less than your P in signal. Similarly, your P out DC will be always less than your P in DC. So do you agree till now? Can anyone confirm? If
Yes,
the
sir.
network is linear, this will be the case. So first thing what we understood, that if we are using a linear network, then there will not be any power amplification. Okay. So first requirement is there has to be non-linearity. And when we are talking about linearity, always remember to simply think linearity in terms of that the relation between input and output. Okay, we are not discussing about any other thing. Linearity is always to be understood in a way that how the relation between input and output are there. So in a BJT, where does that nonlinearity is coming from? What is your input in BJT? Let's say your VBE. What is your output? Let's say you take the IC as your output. So your IC will be some saturation current times e to the power VBE by your thermal voltage, right? I am ignoring the -1 part. So this is your output. This is your input. This part is your input. So there is a nonlinear relationship that leads to ultimately the amplification what we see in the device. Okay. Having said that, what does nonlinearity actually mean? So you have everyone is comfortable with what do I say? Fourier transform. Is anyone uncomfortable with Fourier transform? Then I'll discuss the concepts in a different way. Okay, let me put it in this way. Uh, A sine omega t. Let's say A sine omega t, omega naught t, and this is, let's say, this is the frequency axis, omega axis. So can anyone tell me what is the how will the Fourier transform look like? Guys, this is a discussion session, right? So you should be able to discuss. There is no harm in if you are giving any wrong answer, or if you, it's just a discussion session. I told you in the last class that treat me as a classmate of yours and let's have a chat, right? So anyone can unmute
Just
and just that
omega naught.
you will have a delta function at your omega naught, another delta function at your minus omega naught, right? You keep unmuted. Is that so?
Yes, sir.
Okay. So now what about the magnitude of this plot? What will determine the magnitude? Yes, magnitude will be determined by the this quantity, right? Now you assume that you have included some DC power, right? So where will that DC power lie? What is the frequency of DC?
No frequency or
It will be at
zero.
zero,
It's at
right?
infinity.
No, no,
Uh,
DC has a frequency of zero. Okay. So what do we want to amplify actually? We want to increase these signal levels, these power levels of this signal in time domain, in frequency domain, powers. are same, right? Parseval's theorem. So we want at these frequencies power to increase. Now, if we have a linear network, understand this very carefully. If we have a linear network, then there will not be a frequency translation. That means any nonlinear function, you can Taylor expand it, right? Let's say f of around, let's say you want to expand it around a, right? So you will have a f of a, then you will have a f dash of x at x equal to a, x minus a, then you will have a f double dash of x at x equal to a, divided by factorial 2 times x minus a square, right? This is how a typical nonlinear function looks like. Okay, now this is your linear stuff, right? If you draw just this versus this, input x versus f of x, and if you ignore these terms, then your this quantity is just a straight line, right? Y equal to mx plus c. But when these second order terms start to come into picture, then what will happen? Your input, let's say in this case, x is equal to a sine omega naught t. So if I have some kind of x square, then sine square will produce a frequency of 2 omega naught. So it will start to produce your harmonics at 2 omega naught, then minus 2 omega naught. Then if we have third order term, then other things. If we have other frequency, then things will get intermodulated. So the purpose of saying this is that nonlinearity is required for what? Transferring power from one frequency to another frequency. Do you agree with that statement? Nonlinearity is required to transfer power from one frequency to another. Okay. In amplifiers, what do happen is that the power you are having in DC, this gets, if we do the rigorous mathematics, you can see that it gets to your input signal power, and that's how you have that power amplification at the output. Okay, so your bias, what you apply, that is providing the additional energy source. Otherwise, if you do not have nonlinearity, then obviously your output power of the signal will be lesser than your input power signal. So this has to be, this is somehow transmitting to this into via what? Via nonlinearity of the input and output of the device. So nonlinearity is essential for amplification of small signals. Okay. One point is that. Another point is, why do we choose forward active mode? So this is, we have discussed, right? BJT has this inherent nonlinearity and transistor action. That means one terminal, something is happening at one terminal can be controlled by something is happening at other terminal. Okay, this we have discussed in the last lecture. So now, why forward active mode? So what is very special about the forward active mode? Can anyone tell? No, how, why amplification is, amplifiers are operating at that region? If you know, then it is fine. Otherwise, I'll explain. This is a very important concept. Okay. because we will be discussing about amplifiers without knowing why we are biasing it in forward active. This will be kind of a sin, right? So you should know why amplifiers are biased at forward active. So what is the basic take on that? Okay, just let me explain. So let's say you have a network, right? Can I express my transistor in this form? Can I do that? This is your one terminal. Let's say this is your emitter terminal. This is your base terminal. This is your collector terminal, right? So this is simply your common emitter configuration, right? So this box, I am not telling you what is it right now because I will go into a general analysis. So let's say you have a source here. This is your I1. This is your V1. This is your V2. And this is your I2. So this is ultimately a two-port network, right? So I can use any set of parameters, Z parameters, Y parameters, H parameters, ABCD parameters, right? I choose to use Y parameter for the time being. Okay. So my I1 is a function of V1 and V2, and my I2 is a function of V1 and V2. Fine. Now let's assume our scenario, what we are discussing, that we have a I1 something like this. Your I10, that is your DC, and some small I1, that is my the superseding this signal, this small signal that will be riding on top of that DC bias, because that is what we want to amplify, right? What I am speaking right now is the small signal. If you can convert it to electrical signal, the recording of the sessions are available in the NPTEL website. You can go there and check under the problem solving session downloads. Okay. So similarly, your I2 will be, let's say, I02 plus delta I2. Okay. And your V1 will be, let's say, V10 plus delta V1, and V2 is your V20 plus delta V2. Okay. We will just simply plug these things in these equations. So what will we have? We will have I1 equal to F1 of, what is your V1? V10 plus delta V1, comma V20 plus delta V2, right? So can anyone do the Taylor expansion? It is simple, right? It is just V1 into V10 V20. Then we have the cross terms d F1 over d, what was that, V1, d V1 at V1 equal to V10 times delta V1 plus dF1 over dV2 at V2 equals to V20 plus delta V2. This same formula I am using, right? This same Taylor series expansion I am using. And your this is I10 plus delta I1, right? So this thing will get cancelled, right? Because this is from this equation, if I just put I1 equal to I10, so this will be the case. So your delta I1 is what? This is defined as your Y11 times delta V1. This is your Y12 times delta V2. These are your Y parameters, okay? Then if we do the same thing for I2, I will get this equation. So the important thing in this analysis is to remember that this Y11, these Y parameters are nothing but the derivative of the function or the input output relationship around that DC voltage. Okay, this thing you have to remember and this thing you have to understand. So now if I take same network and connect it in a real world scenario, for example, this is your RL, let's say this is your V source, this is your R source, and this is connected like this, the same network or the same BJT for that matter. That is your Y11, Y12, Y21, Y22. These are nothing but the derivative of the current with respect to voltages around that bias point. So now let's say this is your I1, this is your I2, this is your V2, and this is your V1. Okay. So what do we have? We have your I1 is equal to what? I1 is equal to Y11 V1 plus Y12 V2. I2 is equal to Y21 V1 plus Y22 V2. And what do we have? I2 is equal to what? Minus V2 by RL. I can write it simply GL in terms of in terms of conductance. GL is nothing but your 1 over RL. And similarly, what is your I1? I1 will be your Vs minus V1 times your GS. And what is your GS? GS is your 1 over RS. Okay. So from these equations, can you solve V2 over Vs, which will provide me the ultimate gain actually? V2 over Vs, if you see, it will be something like this. Y21 over GS, and if you manipulate the equations, you will have a term here, this Y21, Y12, then you will have Y11 plus GS times Y22 plus GL. Okay, so this is your final voltage gain what you are getting. So to maximize this voltage gain, what is the condition on these parameters I should have? For simplicity, let's assume Y12 is equal to 0. Okay, why Y12 equal to 0? What is Y12 basically? Y12 is your this action, means when your, what is Y12? Let's discuss. Y11 V1 plus Y12 V2. So this has to be 0. V1 has to be 0. V1 has to be 0 means what? V1 has to be short circuited. And in that case, your Y12 will become I1 by V2. That means if you short the input port, whatever voltage you are giving at the output terminal, what current is coming out of the input terminal. Okay. So if there is no feedback, we can assume safely that it is 0. For our discussion, we will assume that Y12 is 0. Now tell me what is the condition on Y11, Y22, and what is the condition on Y21? It should be 0, it should be infinity. If you want to have a higher gain, V2 by Vs, from this equation, please tell me that. Unmute and tell me. It is just simple. And assume that this minus sign, assume that it is modulus. We are discussing about the modulus. That we want to increase the gain of the amplifier. How do we do that? Let's take Y21. What should Y21 be? High or low?
Low.
Y21, why should it be low? I want to increase this, right?
If you want
Y2,
to increase that,
this
denominator
term,
should be
no, no, this
high.
term is not there. This is 0, right? If I want to
Okay.
increase that, numerator should be high, right?
High.
So numerator, I have Y21. So Y21 should be high, right?
Yes, sir.
So Y21 should be high. Ideally what? Infinity. Then I can get infinite gain. Okay. And what about Y11 and Y22?
Should be low.
Should be low or should be close to 0. Right?
Yeah.
Now let me take you to the BJT parlance. Now let me take you to the BJT parlance that, by the way, what is the input port in the BJT? For our case, let's say port 1, that is input, in our case is B, and port 2 is collector. Okay. Let us assume that we are discussing about the common emitter kind of scenario. Okay. So how does your IC versus VBE look like, and how does your VCE and IC look like? So this plot is just like a diode, and this plot is something like this. Do you agree? Have you seen these plots? Anyone?
Is it IC or IB?
IC and
IC or IB in first case?
IC is equal to beta IB, right? That is the same thing. This is your output current. Means your, in our notation, it was I2. And this is your what? This is your V1. This is your V2. And this is your I2. Fine. So what is your IC? IC is equal to IS times exponential VBE over phi t, isn't it? So I can draw this plot, right? Is it okay for you guys?
Yes, sir.
We are going to a very interesting part, that how do we choose the bias point for amplifiers, right? So ideally, from this equation and this consideration, how do my I2 versus V1 and I2 versus V2 should look like? Ideally, it should be, what is my I1, I22 ideal is 0, right? So what kind of line I should have? If I want to have Y22, what is Y22? Y22 is nothing but your derivative of I2 with respect to derivative of V2 at the bias point. I want to have this equal to 0, right? So that means I need to have a straight line or something close to, very close to straight line, because in this line at any point, if you take the derivative, your di2 by dv2 will always be 0, or your y22 will always be 0. Do you see? Is anyone unable to understand this? Because this is very critical. that how should your I2 versus V2 profile look like, and how should your I2 versus V1 profile look like for you to have a and good amplifier. Similarly, in Y21, what it should be? It should be infinity, right? That means I should have a straight line like this, vertical straight line. What is the slope of this line? At any point, di2 by dv1 is equal to infinity. It's a vertical line, right? Slope is infinity. Horizontal line, slope is 0. Are you getting this? Can anyone confirm?
Yes, sir.
So, if you are agreeing with that, please tell me where should I bias in my BJT for a good amplifier, right?
Forward active.
So forward active means I should bias my BJT in a region where the slope of output characteristics, this is called output characteristics by the way, slope of output characteristics is 0, right? Because this is what is desired. This will give me, this Y22 will give me what? This IDIC by DVCE. This will give me my Y22. So I need to have my bias point somewhere here. Do you agree on that? Ideally, what should I have? I should have, this is very straight. I want to have this slope of this line very low. Then I will have a good amplifier from our derived theory, right? And where should I bias my input side? I want to bias my input side where the slope is very high, right? So around this region, okay? Because your DIC by DVBE will give me what? Will give me my Y21, right? This is called, by the way, transfer characteristics. So I want for a good amplifier, my bias point to be at this point and somewhere around this point. So what is this region? Beyond this, it is nothing but EBJ is forward biased, and in this case, your CBJ is reverse biased and your EBJ is forward biased. So this is your forward active, right? Now, if I ask you that, or if in that matter, if anyone asks you that why do we need to bias my amplifiers in forward active, will you be able to answer this question? You are not audible, Aban. Can anyone else
Yes, sir.
confirm? So you get the point, right? Shiva, is it?
Sir.
So this concept we will take to our MOSFET analysis also, right? You will see that in MOSFETs also, you bias the device in the active region. This region is called active region in case of MOSFET. What is the reason? Same reason, same analysis, that you need to have your Y22 closer to 0 and Y21 closer to infinity for a good amplifier. Then you can increase your V2 by Vs. Okay. So this is the reason why we bias our amplifiers in the forward active region. Okay. So if you did not get the point, please go to the recording session again and try to get it slowly. So yeah, let's move on to the next problem. So what does it tell? At the beginning, electronic students is just learning about transistors and reads in the textbook that a bipolar transistor can be thought of two diodes connected back to back as such. True. On that this acting on this idea, the student proceeds to connect two, these are PN junction diodes, rectifying diodes back to back and try to use it as a transistor. The idea does not work, although the diode pair reads the same pattern of continuity. Because this is same pattern of continuity and it does not amplify. Explain why. So can anyone answer that? Why does it happen so? The question says that you have a BJT, right? Let's say for the change of test, let's say this is PNP. So what do you have? You have one junction here, another junction here, right? This is your EBJ, this is your CBJ. So you have basically this kind of connection. And what they are telling that in lab you try this one. This is your PN, then this is your PN. You connect it like this and you connect these things and take another point. So this is your base, this is emitter. Let's say this is collector. For the sake of notation, let us be consistent. Okay, so you connect it like that. So this amplifies, this does not amplify. Why?
The base region should be very thin that the velocity of that electron should pass through that barrier and
Velocity.
forward to the collector. It
Velocity
means
is not
movement,
a right term. Yeah, you are very close. Actually, I am very impressed with the answer. It is actually the reason, but
movement.
there are little bit information missing. By the way, can you tell me that why does BJT amplify? This we have discussed in the last class, but again, I just wanted to. Okay, let us put it in this way. We had PN junction, right? We had PN junction in our lab. Now, how did people thought that we should have a third terminal connected? Means, how do people first thought that PN junction to BJT there can be an amplification? What is that thought? Have you ever think of this that we have the PN junction theory? Now we have a BJT. What should have been the thought process behind that? That this can be done because that's how they have invented, right? So for that matter, if you want to win a Nobel Prize in later in your career, you should have those kind of thought process that how one thing was derived from the other. For example, let's take a PN junction. This is P, this is N, let's say, and this is the depletion region. So can you tell me what are the current profile? Let's say this is your this line is your zero line. This is your total current, right? Let's say this is your J, total current density is constant. By the way, J is constant. What does that imply? This is your X. This is total current density in PN junction. So J is independent of X. What does that imply? See, you are learning new course. You are doing new course, right? You should not forget your old courses, and you should not forget the bridge between these courses, right? This should always be in your mind. So, can you please tell me that if J is constant with respect to position, what does that imply? Anyone?
Maybe the electron density is linear, like slope, man.
Irrespective of any electron density, if I just give you any material, not even semiconductor, any material, if I give a block and I tell you that your J is constant with respect to X, what does that imply? Have you heard of this condition of steady state? So this implies that you are in a steady state condition. Okay. Now, okay, leave that. Tell me, how does your my elect there will be currents like this, right? There will be electronic current, there will be hole currents. So how does those currents look like? For example, in N type, this will be my current. What current is this? Let's say this is my JP. Minority carrier will diffuse and my current profile is exponential, right? Similarly, I will have my Jn in this side, and for the time being, let's assume that there is no what in the base region, and then this will be just your J is what? J is your Jn plus Jp. So this will just follow this and reach your J. Similarly, this will follow this and reach your J. So this is your majority carrier current in N side, and this is your majority carrier current in P side. So are you guys familiar with this plot? Have you ever seen this plot in your PN junction course? Have you seen this plot? You haven't seen. Yeah, now I am surprised. Okay, someone is telling that you have seen. So, by the way, how does current flow in PN junctions? What are the mechanism, right? I have told you earlier today that your this is your what? This is your N side. This is your P side. So electrons will move from this place to this place. So once electron move at this edge, right? How does electron move in P type region? Who was that? Adav Gupta. Can you please unmute? Adav Gupta. Okay, mic is not working. Okay, then how will we discuss? Okay, think in this way that your electrode is injecting electrons, you are having a forward bias, your barrier difference have reduced, so more number of carriers can flow. Once it crosses its own territory, that means once this electrons crosses N type to P type, in P type it is a minority carrier, right? And how does minority carrier moves in a in a material, minority carrier will obvious because there are less number of electrons and too much number of holes in p type, so they will eventually recombine. This process, what we call minority carrier, diffuses, right? Diffuses and recombines in what time frame? During its lifetime, around its diffusion length. Okay, these are the basic physics concepts which you should have before joining this course. Okay, if not, please revisit and check that this is a very standard plot. These are the current contributions in the PN junctions, right? So now I want to get amplification. So what thing should I have? I want to have a certain mechanism by which before this JP recombines completely, if I can get it into another region where it is a majority, then I may get some amplification, some sort of amplification. And how do we do that? By connecting another p-type material just adjacent to it. That means now what I have, so this was my depletion region. So this is my p plus, this is my n plus, then this is my p. So I have added this additional region, right? Now what happens is that in the base region, so far we had drawn this diagram in this format, right? This is PN junction, this is something like that, and we had this, and this. So this part we have seen here. Now we want to have these carriers cross over here and become a majority carrier so that it can contribute to the bulk portion of the current, right? One thing you notice throughout in this plot is that your majority carrier current is always higher than your minority carrier current, right? In, for example, in p type, you can see that in most of the bulk region your majority carrier current is much higher. So there is a one sentence we learn in our undergrads, that minority current in PN junction flows due to minority carriers. That is not true. The profile of the current in PN junction is dictated by the profile of the minority carrier current in respective regions. But the majority portion of the current, as you can see from this plot, that the magnitude wise majority carrier current is obviously carries the bulk portion of the current or the major chunk of the current. So I want to have some mechanism where I can make these holes a majority carrier in a region. So I have attached a p-type material adjacent to that PN junction, so that once my holes are injected in this place, they are starting to recombine. Before recombination, they cross and becomes majority carrier in this p-type region, right? So what are the consideration we should make? One very important consideration is that this region or this electrical base region should be very narrow. Why should it be narrow? Then my not all of the holes that is in this n plus region, that are the minority carriers, do not recombine. Before recombination, they just cross over and becomes majority carrier in collector. Okay, so this is the primary reason behind the thought that how PN junction can be used as an amplifier, and then the concept of BJT came into picture. Okay, now what is the important thing, that in base region we must not have all minority carriers, in our case it is holes, recombined, right? So we cannot allow all the minority carriers in this region to recombine. So one way to do that is to reduce your base width. Okay, that is why we have a very narrow base in the BJTs. Okay, now coming back to our question, in a PN junction, okay, just let me take this. In a PN junction, why do you think that JP in this place and JP in this place and JN is this place becomes 0? Which part do you want me to repeat? Okay, about BJT. So my, okay, just let me draw it again. So this is my base, this is my emitter, this is my collector. Let's say this is P plus type, P type, this is N type, and this is P type. Okay. Now you have this junction forward biased, this junction forward biased. So holes will be injected in this region, then holes will cross through, and let's also draw the depletion regions. So holes will cross through this region. Whenever the hole has reached this point or this point, what will happen to the holes? Am I audible, by the way? Can anyone confirm? Okay, fine. So when my holes cross and come back to this N-type region, so what will happen to the holes? These holes become a minority carrier, right? Once these holes become a minority carrier, it starts to recombine. The same thing we have seen in the PN junction. It starts to recombine as we move along the N-type region. So what happens that the concentration of the hole, if you plot the concentration, excess carrier concentration that we call, this excess carrier concentration will start to drop, right? This is your delta P in N region. This will start to drop. So I don't want this all hole to become recombine and become 0, right? I want to send it through the collector junction, into the collector, so that there it can become again a majority carrier. Okay, so the way to do that is that you reduce your base width. Think it physically, you reduce your base width as you keep pushing your collector base junction towards this side. What you are essentially doing, that you are reducing the area for the recombination or the space for the recombination. And how does that help? That helps in how? That helps in reducing the recombination, so that at this point, you have certain amount of excess carrier still remaining, or more essentially, this slope is intact. You want to keep the slope at this point same, right? Why do you do that? Because diffusion current is what? Your excess carrier concentration divided by dx, right? So you want to keep that current as much as conserved as possible, less recombination. So most of holes will move from emitter to collector. Okay, so this is basically your BJT action. So now what I was discussing that in PN junction, why do you think that at the boundary all holes and electrons, respective minority carriers, has to recombine? Why is that? In a PN junction diode, if you plot the excess carrier plots, you can see that all will be zero at this point. It has to be zero. And why it is so? That is the question. Can anyone unmute and able to answer that? Anyone? Why does at the contacts or at the boundary the minority carrier diffusion is complete and there basically all the minority carrier recombines? Why at the boundary all of the minority carriers recombine? That is the question. By the way, what do you think we have at these boundaries? What are these boundaries?
Semiconductor
Sorry? No, no, at these boundaries, what do we have at these boundaries?
like metal contacts.
We have metal contacts, right? Always remember that whenever we are talking about PN junction, there are metal contacts at the end. So why now the question is why at the metal contacts all the minority carriers recombine? This is a very deep question. I just want to know if you know the answer or not. Whenever a semiconductor metal contact forms, there are what? Semiconductor is a crystal, right? So the periodicity will be broken at the boundary. So there are so many recombination centers within the energy band gap. I will not elaborate on this, just hear me out that there are so many recombination centers in the metal semiconductor contact because the semiconductor periodicity is getting terminated. There are so many states through which the electron and hole can recombine. Okay, these are called surface recombinations. So due to surface infinite surface recombination at the metal contacts, all your minority carriers has to recombine at the metal contacts. Right? Now come back to this question. Here, what do you have? You have a metal contact here, you have a metal contact here. You have a metal contact here, you have a metal contact here. Sorry, not here, this place, right? So as soon as you connect two PN junction diode back to back, so there is a metal contact in between. That means if you just connect this thing, just let me copy it. So if you just connect this thing, right, what will you see? You will see a P plus plus, N plus, N plus, and P. But you have a metal contact in between when you connect two PN junction back to back. That means this will act like what? Infinite recombination. That means what? Your excess carrier has to become zero here, right? This excess carrier, what we are talking about, this has to become zero here. So nothing will cross over this junction or this metal semiconductor contact. Okay, so the basic essence of BJT functioning, that you want your base to be narrower so that this magnetic carrier can cross over here and become majority carrier, that opportunity is lost. What happens, this all the minority carriers, whatever is coming from this, all the holes, whatever is coming from this side, gets sucked into this metal contact and gets recombined. Okay, so there is no collector current coming out, so there will be no amplification. So this thing I want you to try in your lab. If you have the access of your circuit labs, you just find out these diodes. It is abundantly available in all the labs. Connect it back to back and try to get the BJT action. You will not get. Okay, and this is the reason. The key reason is that metal contact gets introduced in the base region, that creates infinite recombination centers, that creates all, that makes all the minority carrier in the base to recombine at that contact itself. So it does not allow that carriers to cross over the collector region. Okay, anyone have any question on this? This is a very interesting question, this is not your general textbook question. This kind of questions will be asked in the interviews, in your PhD, MTech interviews, or in your job interviews, in your core companies, right? So whatever the purpose you are doing this course for, these kind of things you should have a clarity, and this comes from the understanding of the how did the device works. Okay, so is that clear? Can I move on? I don't get any response.
Yes, sir.
Okay, fine. So let's move on to the next question. The base current is always the what? What is the answer? This is trivial.
Smallest.
Why? What? By the way, what is the base current? What is the base current? Means why do base current flow in the first place? In this diagram, you can easily tell, right? Why do base current flows? Base current flows because some of your minority carriers will recombine in the base, right? Do you see this recombination current? Some of this will flow through this N terminal and remaining will be sucked out to somewhere in the collector. So this current is basically your due to the recombination in base region. Okay, and how do you do that? Tell me the recombination current formula, in that matter recombination generation current formula. Do anyone remember? Okay, let's do it in this way. I equal to Q by T. Fine. Q times T, and now you integrate it over the volume dx dy dz, or in other sense current is what? Your recombination rate. In silicon it is SRH recombination, then your dx dy dz, right? So if you have you seen the recombination rate formula in SRH? Np minus Ni square divided by some tau times n plus n0 plus n0 plus ni, sorry, n1. This is tau p plus tau n times n. This will be your p0 plus p1. This kind of formula. This p1 is nothing but the trap levels in the band gap and what are the difference of that with respect to conduction band and ei, right? So if you integrate, put it here, integrate this two dimension, you can simply WLN, you can keep it out, or let's say simply you can just make the area outside. So you will get this Q times area times this RSRH dx, let's say dx is the dimension in a PN junction. It will be the same in case of BJT also. So in this region, you will have the depletion, right? Okay. So you will get that recombination generation current. You just plug it in and you will have a formula something like Q W. W is nothing but your this W, okay? Times area W dep, let's say W dep. W depletion area over area times Ni over tau times exponential Vd. Let's say this is the diode voltage applied, Vd by 2 phi t, right? This kind of expression you have seen, right, in your PN junction courses. In your generation recombination current in the depletion region has this kind of expression, and this comes from this derivation. And this RSRH is dominant, or Shockley-Reed-Hall is dominant in the silicon or indirect band gap kind of materials where the doping is moderate. As your doping increases, what kind of as my doping increases to, let's say, degenerate level, what kind of recombination dominates there? Anyone? So you must have heard of OZ recombination, AUGER. OZ recombination dominates in case of degenerate semiconductor. And what about let's say my material is not silicon but gallium arsenide? Then what should I use? It is a direct semiconductor, right? So direct band-to-band recombination will happen, right? And energy will be released via photon. In this case, energy released via phonons or heat for that matter. Temperature will increase at the lattice side, and your these particles we called it as phonons, and in gallium arsenide photons will be released. So basically the purpose of telling is that this formula you have to change accordingly, right, while you want to derive the this expression. This is for silicon semiconductors. So you see that this is dependent on Vd by twice phi t, and what are my I C and IE? These are dependent on exponential VBE over phi t, right? So obviously this rate will be lower. So essentially my recombination current or base current in the given range of bias where we operate our devices are smallest. Okay. So let's move on to the next problem. So your beta is of the transistor. Beta is nothing but your IC by IB is given as 60. So they want us to find out alpha. So what is alpha, by the way? Means what is the significance of alpha? I mean to ask that. What is alpha in this case?
The ratio of IE to IC.
Ratio of IC to IE, right? And it depends on two things, right? Gamma times beta. Gamma is your emitter injection efficiency, and this is your base transport factor, right? So what are these? Just let me tell you briefly. So this is your EBJ, this is your CBJ, right? So let's say this is PNP. Again, I want to be specific because it helps you keep in mind that what kind of doping you generally have in your BJT. So holes are injected, right? Holes cross over, then holes diffuse here, then crossover, then this becomes your ICP for holes. This is your IEP. This is your IE. Okay. Now what are the other things happening? Electrons are getting injected in this place, and in this region your holes and electrons are getting recombined, right? Again, it is a PN junction, so electrons will be injected in this location also. So some holes will be recombined in this place also, right? So this constitutes your recombination current IR. This constitute your IEN, right? IEN is the current due to the electrons in the emitter. So what are the current direction, by the way? This is electrons flow. So current will be this direction, this direction, and this direction. So if we use KCL at this point, we have what? IE is equal to IEP plus IEN. So what is my gamma? Gamma is nothing but your IEP over IE, that is your IEP over IEN plus IEP, right? Similarly, this is your IEP and this is your ICP. Let's say ICP is itself IC, and being it being in a reverse bias, your this current component of your electrons is negligible for the time being. Let us assume that. So what is your IC? Applying KCL at this node, IC is nothing but your IEP plus IR, right? So your base transport factor companion node. Achha, okay. So your base transport factor is nothing but your ICP over IEP, right? So now you want to define your alpha, that is your IC over IE. What you do? You do it in two part, IC over IEP times IEP over IE. This is your B, this is your gamma. So to increase your gamma, you generally do what? You generally dope emitter heavily with respect to your base, right? And to increase this beta, because both has to be increased, this is multiplication, this alpha I want to increase. So this beta, what you do? How do you increase beta? This beta is basically will be increased if your IR can be reduced, right? If your IR can be reduced, that means your base need to be narrower. So these are the design considerations from the technology point of view, that how long or thick you want to make your emitter base and what should be the doping. Okay. So doping wise, what we see that doping of emitter is greater than doping of base is greater than doping of collector. And what about the width? Width of collector is greater than width of emitter is greater than width of base. Okay, this thing you please remember and try to understand why it happens so. Okay, so now what can we conclude from this? that you know that my IE is equal to IB plus IC, right? So now if I just make IE by IC and divide every side with IC plus 1. So what is this quantity? 1 over alpha. What is this quantity? 1 over beta. What is this? So they want us to find out alpha, right? So 1 over alpha is equal to 1 over 60 plus 1. That means your alpha should be 60 over 61, right? Which you will get as 60 over 61, you will get as 0.9836. Okay. So if beta is given, you can easily find out the alpha. But don't only solve the problems in terms of numbers. Okay. Try to visualize what is happening inside the device. Then only you will be able to comprehend the entire material. Okay. What is happening and how it is happening. So let's move on to the next problem. Okay. Base width modulation occurs in a BJT operation in this. What should be the answer? And what is base width modulation, by the way? Anyone?
The deflection region is so wide that it will eat out that base uh,
Right. Absolutely right.
region.
But why does it happen? And what is the consequence of that? The consequence is that, let's see, this is your PNP transistor. Okay. So what happens is that, again, what did I tell you earlier, that I want my amplifier characteristics is to be, what is the ideal I want? I want this to be this, right? The slope I want is 0. What do we mean by slope is 0? That means whatever VCE I apply, it should not control the current, right? For example, if my device is biased at this point and if I have a small signal on top of that, so what should be my ID? It should be 0. My Y22 should be 0, right? This is my desired property. But what happens in reality is that this slope is never 0. It happens this. So slope is greater than 0. What does the implication of slope is 0? That means your IC is now controlled by VC to some extent, right? But do we want that? We do not want that, right? We want our this junction to control this junction. We do not, if my VC starts to dominate, for example, let's say if my if VC starts to dominate in determining IC, what kind of device it will be? First of all, it will simply act like a resistor, right? You see, this is a IV characteristics and you have a linear region. That means you will see only a resistance. It is nothing but this stuff. Let's say this is your VC, this is your VB. So if you are sweeping VC, your current is changing, right? That means it is simply a resistor, nothing else. So you do not want that. You want your EBJ to control the characteristics of your CBJ. Fine. Now what is base width modulation? For example, what is the condition of bias in this region? The condition of bias in this region is forward biased, right? And what is this? Reverse biased in my forward active region. Now assume that my in reverse bias what is happening, this depletion region starts to expand, right, as I increase my VC. Do you agree that in reverse bias the depletion region of the PN junction increases? Anyone, can you confirm?
Yes.
So what happens is that, so this portion is also getting eaten up by the collector voltage, increase in the collector voltage. So what happens, this your minority carrier starts to decay very fast, or in other word, let me just correct my statement, that minority carriers in this region maintain the slope. That means whatever current you are injecting here, more amount of current is getting into the collector, right? Because what is happening, this exponential nature e to the power minus x is now becoming a linear, that is 1 minus x plus x square by factorial 2 minus x cube by factorial 3. If x is your smaller, then what, this quantities you can ignore. If x is much less than certain, let's say alpha, certain small value, so this becomes a linear profile, right? In linear profile, the slope at this point are same. That means the current I am getting in this position and the current I am getting in this position are same. That means what, my IC is approaching IE. That means what, my IC is increasing, right? So as my W, if this is my WB and this is my WB dash. So as my WB dash, or the electrical width, the available base width starts to decrease, my IC will start to approach IE, or in other word, IC will increase. And that is controlled by what? That is controlled by your collector voltage. That means this collector voltage, as you increase, so you will see after a certain point there is an increment in the IC also. This increment in the IC. So this mechanism is called your base width modulation. So this is not desired for us. Why? Because we want our slope to be 0. So what is the remedy of that, or what is the solution of that? Solution is that in a PN junction, if I give you a PN junction, let's say PN, and let's say I am giving you a doping around 10 to the power 18 and here is a doping around 10 to the power 16. So what is the, okay, just let me ask you numerically. So this is your WP, this is your WN. So what is the ratio of WN by WP? Anyone?
Sir, am I audible?
Yeah, you are
Hello.
audible.
Sir, I was saying, what is the meaning of like doping 10 to the power 18? Like, what is the actual meaning of it?
10 to the power 18 means doping. You want to know the meaning of doping?
Yeah, no, 10 to the power 18 centimeter cube. Like, at every 1 centimeter cube, there is 10 to the power 18 doping.
Yes. Or you can say in a different way that, okay. Okay, I'll come back to you this point. Okay, just to hold it for a moment. Let me just complete this part. See, this your WN by WP will be what? WN by WP will be your 100, nothing else, right? Because the lighter region in the PN junction will get more depletion width. Ultimately, guys, you need to maintain this charge neutrality, right? You have 10 to the power 18. This is what? This is your minus, this is your plus. So 10 to the power 18, this charge, and it will be somewhat this, right? This is your 10 to the power 16. And this is your, let's say, 10 to the power 18. I am talking in log scale. So obviously this area and this area has to be same, right? This we read first thing in the PN junction. So what happens? This Wn has to be much larger than Wp. In what ratio? That my Wp into 10 to the power 16 should be equal to Wn into 10 to the power what? This is 10 to the power 18. 10 to the power 16, right? So my Wn by Wp will be what? Nothing but 100, right? So what happens that depletion region is larger in the least doped side. So if I want to reduce the impact of reverse bias on base, my collector doping, this is in, let's say this is collector doping is PC and this is your NB. So my collector doping PC has to be much lesser than NB. Then most of the depletion, if I increase the reverse bias, will be happening in this least doped collector region. Do you agree? This is the reason behind least doping in collector. So can anyone confirm that they have got this point? What is base width modulation, why it is not desired, and how can we get rid of it? And this obviously happens in your forward active region, right? This is your forward active region. So are you with me, guys? Anyone have any problem understanding this part? Okay, if not, so let me answer his question. So what is doping, right? Who was it?
Yes, sir, me.
Yeah. So can you tell me what if, okay, just let me write it here. What is doping? Okay. So first thing is that your silicon is a crystal, okay? So do you know what is the distance between these two atoms in silicon? What is this called? Lattice constant, right? It is
Yes, sir.
5.43 angstrom, right? What is angstrom? 1 angstrom is 10 to the power minus 10 meter. Fine. So in 1 cubic centimeter, how many atoms of silicon are there? It is around 10 to the power 22. Okay, 10 to the power 22 silicon atoms are there in 1 centimeter cube volume of silicon. Okay, now what is happening? You are, let's say you have some gun here through which you are starting to ion implant or diffusion. By diffusion process, let's say you are trying to dope it in p type. Okay, so what are the material you should use? Trivalent material. Give example of an trivalent material. For example, let's say boron, right? And you are doping it with 10 to the power 18 per centimeter cube. What does that mean? That means that in 1 over 10 to the power 4, that means 1 over 10,000 silicon atoms, you will have one boron atom. Okay, this will just knock out this silicon, and this is called what? This is called your substitutional site. That means one boron atom is substituting one silicon atom from its lattice. Okay, so these were all the bonds was there right earlier. But do you think that only substitutional sites are there in the system, in the material? There are these voids also, right? These voids are also called interstitial voids. Borons can occupy those places also, but that is not our concern. To have the chemistry and all the chemical bonding, we need to have the boron atom in the silicon substitutional sites in the silicon lattice, right? So 10 to the power 18 doping means that 10 to the power 18 over 10 to the power 22. That means in 1 centimeter cube, you will have 10 to the power 18 doping means in 10,000 silicon atoms. Among 10,000 silicon atoms, you will have one boron atom. Okay? And that boron atom will do what? Boron atom is trivalent, right? It will capture an electron leaving a hole behind. So this hole will can now roam around. This is called free carrier. Free means it is able to around in your silicon, what do you say, silicon potential. If you see your dopings, it is, if a nucleus are like that, so it is something like this. When multiple atoms are there and we have a big place, so now one, if you substitute here one this location with a boron atom, so one hole gets out and it gets a much wider room to roam around. Earlier it was just trying, was getting tied to the nucleus. Now it gets a larger potential room to roam around. This is what is happening in the doping. Okay. So does that answer your question, or do you have anything more in depth you want to learn about this? We can discuss. You can ask question.
No, sir, got it.
Okay, fine. So
Thank you.
similarly, your N type is also there, P type is also there. So this is, we call it that it is a notion of understanding that what does 10 to the power 18 per centimeter cube means. Always keep it in your mind that it means in 10,000 I have a one boron atom. And what about P type 10 to the power 16? That means what? 10 to the power 6. That means what? In 10 lakh, right? In 10 lakh silicon atom, I have one, let's say your phosphorus. Okay. So this is how you should understand and visualize the doping. We can go much deeper into quantum mechanics also, but that is not the purpose of this course. In the first lecture, in the comment section, I have mentioned one of my previous previous courses where I discussed the quantum mechanics in detail. Okay, for any in-depth discussion on the band diagrams or on the this semiconductor physics, you can go there and check out. Even band diagram in quantitative measures also have been discussed there. Yeah.
Sir, to like in much of things I didn't understand the concept. Like to study this course, is semiconductor physics important to learn?
To certain extent, see what is that's a very good question. Semiconductor physics to a certain extent, by the which you are a PG or UG?
I am in final year of
Final year,
PG.
final year PG
Yes, yes.
in
MSc,
which
MSc in electronics.
MSc in electronics. Okay. So see, so what I should expect from you is that you should at least read some standard device physics books. Okay. Because see what we do, I can skip all these discussions and simply go to the circuit formula because that is what I am planning to do from the next class. But given that, you should have the basic understanding of why things are happening, right? You should not lose the sight of what is happening in the background. Just like you have asked about doping, right? It is a very trivial question that what is doping, but we do not even consider always that yes, it is the 1 in 1000, 1 in 10,000 atoms of silicon, there is one phosphorus, one boron atom. So I suggest you that at least you should be thorough about what is PN junction, what are the band diagrams, what is BJT, what are the mechanisms of BJT that is going on. Because the first week lecture, Professor Dasgupta has taught about on, he has briefly touched on the basics of the device physics, and then he moved on to the various configurations of the BJT in circuit parlance. Okay. So what I expect from you is that when I start the discussion or the other TA starts the discussion in the Monday, so you ask your doubts regarding those kind of concepts if you have any. Just like you have asked me today about this doping thing, right? There will be many more concepts which may be advanced for you then that you did not grasp about. So try to search those in Wikipedia, try to see, or if you can comment on the YouTube video that give me content from where I should learn this. I can give you other lecture video, other professors lecture video links, Professor Dasgupta's other lecture series links, or some books or some notes, right? So do that homework. Otherwise, it will be difficult for you to follow because once you are in the circuit parlance, you are given something and it's just KCL and KVL, right? But if you want to create some or synthesize some interesting circuits, then you need to know what is diode connection, etc. This we will discuss in next lecture. Okay.
Okay, sir. So what are the resources, sir?
So what there are, see, there are let me say tending to infinity kind of resources. What topic you want to learn, that you have to be very specific about. So what I am doing is that I am just putting my email ID in the chat box. Okay, you just mail me that what content. For example, you want to learn about PN junctions, right? PN junctions has multiple facets. You have electrostatics, then you have transport, then you have small signal analysis, then you have transient analysis. There are many aspects. So, what particular thing you want to learn about, that you should you mail me and I'll give you the resources. Is that okay?
Okay, sir.
Okay, fine. I have a doubt regarding the pattern of analysis of this. Yeah, this I think you need to discuss with the NPTEL team. Just email them, or in the discussion forum, there is a discussion forum in the Swayam portal. You just raise a question there. I think the team will be able to answer that. Okay. So yeah, thank you guys. Let's end the session here. See you in next Sunday.
Sir, there's one more doubt.
Yeah,
So in the top, sir, BJT.
yeah, right. Go on.
So,
Still above that. Which one?
sir, this one. Sir, we are
Okay.
thought that. Sir, we were told that the base, the width of the base is small. Like with the largest width is of emitter, then collector, then base.
No, no, largest width is of collector, right? Because you have all the carriers to get recombined.
Okay.
So
And
collector has the highest width, then you have your emitter, then you have your base. Base has the smallest width.
so we have see by symbolically we used to design BJT like this in a triangular
Mm,
perspective.
where do you see triangle?
Rectangle for rectangle purpose.
This one, or this
Yes,
one,
sir. Towards the right.
this one.
I'm not able to see the cursor.
Okay. Just hold on. So this one or this one, which one?
This one, right one.
This one.
Yes.
Okay. So what is the
So like
question?
question is that the in the B like BJT is taking the lot of area, no? B
BJT. See,
sorry,
okay.
base base is having a big well.
So what is the meaning of area now? I have not discussed the area dimension here, right? Area, when you consider this, it is in this dimension. Okay. This area
Yes.
is your, on top of that, if you look from the top, then you are concerned about what is this. This is your basically length dimension. This is your width dimension. So this W cross L you are concerned about. This is the silicon area what we talk about. We are not at all concerned about this vertical direction. That much space we have. Okay.
Okay, sir.
So when we talk about the area we talk about always the top view. What is the W and L? For example, if you have seen the what do you say? If you have seen a MOSFET, right? So this is your MOSFET. This will be your MOSFET. So on top of that, how does it look like? It does look like simply like this. This is your source, this is your drain, and this is your gate. Okay, this area we are talking about. This is your length and this is your W. So this area should be minimized. That is the point, not the vertical dimension. Okay.
Okay, sir.
Okay. So okay, let's end the session here.